So hello everyone, myself Sumit Yadav,
Hello everyone, my name is Atharv Derdekar.
and we are having a subject of transport phenomena, and we have a topic of flow through circular pipe. So in the chemical industry or in food mechanics or moreover in the transport phenomena, we basically see a lot of type of flows like flow on a duct, flow on a flat plate, flow inside a circular pipe, or flow perpendicular to a circular plate or tube. So basically, we're going to see or consider firstly the circular flow through the circular pipe in this video.
So in real world scenarios also flow through pipe play a crucial role. So what we are doing in this video, by the help of engineering correlations, we'll analyze the flow through pipe phenomena by using engineering correlations like Dirac-Volter correlation. So for different scenarios, we have different correlations. Just as I said, Dirac-Volter correlation is the correlation used in determination of heat transfer coefficient. Similarly, we have CD equation for determination of heat transfer coefficient. Now, coming to mass transfer coefficient, we have Linton-Sherwood correlation, Gilliland-Sherwood correlation. Coming to friction factor determination, we have Colebrook-White equation. So for different phenomena, we have different equations which are applicable in different situations at different temperature ranges, different pressure ranges, different dimensionless number ranges. So we'll use them in our questions to analyze the situation given in it so that we can understand more about flow through pipe.
And as we see every picture of a chemical plant or a chemical industry, the flow through pipe or uses of pipe is very important because play a very crucial role like through the transport or like any chemical reaction or any physical phenomena. So basically, if we talk about the equipment, so basically CHDR, the continuous rotating reactors, there we see the application of this flow through cylindrical pipes or circular tube. The PFR, plug flow reactors or circular tube reactors, heat exchangers, and drainage pipes. So there we see the application of these flow through circular pipes. So that means they are very important according to the. So let's see the applications of that by the help of some problems.
So here we are having our first problem. So it is basically an industrial problem. So the problem is like that air is flowing inside a pipe which is having a diameter of 1.5 centimeter internal diameter and a very minimal thickness of the pipe we are having, and the air is flowing with a velocity of 50 meter per second, and the initial temperature, the temperature at which the air is entering, is 20 degrees Celsius, and a steam is flowing over the pipe in which the air is flowing to raise its temperature, and the temperature of the steam is given is 150 degrees Celsius, and we are given with some data that is at bulk mean temperature which is 55 degrees Celsius. And the first part of the question is to calculate the length of the pipe required to increase the air temperature to 90 degrees Celsius. So the initial temperature of air is 20 degrees Celsius and the steam is at 150 degrees Celsius. Steam is transferring its heat to air. So we need to find out that how much like the contact length of the steam and air is required so that the air temperature should be raised to 90 degrees Celsius. So this is the first part. And the second part is like discuss the effect of surface roughness on the length of the pipe. Like when we find out the correlation of friction factor and the length of the pipe, then we need to relate the surface roughness, that is E by D, that we find out from the Moody's chart. So we need to correlate with the length of the pipe. Okay, so this is the different part of the question, and now we are given with some data that is at the mean molar temperature, that is 55 degrees Celsius, and the like the air property of air is given, the density, the viscosity, the kinetic viscosity, Prandtl number, and other things are there. So let's start the solution.
So this is basically the schematic diagram of the question that we are having. So the air is there which is entering at the temperature of 20 degrees Celsius at the speed of velocity of 50 meter per second. Okay, and now we are having the length of this heat exchanger L that we have to find out, and the air should release here at the end at 90 degrees Celsius. Okay, and the steam which is providing the heat, the convecting heat to the air to raise its temperature from 20 degrees Celsius to 90 degrees Celsius is at 150 degrees Celsius. So steam is entering and now the steam is condensed from that side. So now in this question we need to find out the length of this heat exchanger so that the temperature of air we can increase it from 20 to 90 degrees Celsius.
from one side to another side. So the basic approach of this question is that we can go from mass balance and energy balance. So the basic approach is we can go by the energy balance and mass balance. So across this heat exchanger, we can write the mass balance, that is the total mass inside going inside the system is equal to total mass going outside the system. Because this is a like a continuous process, so there is no addition of masses there. There is only addition of heat or energy we have seen here. Like the steam is losing its energy and giving to the air, and steam is condensing out from one side, and the air temperature also increases from the another side. So first of all, we are going to write the mass balance. Okay, so mass balance is there. So total mass going inside the system is equal to total mass leaving the system. Okay, so we are basically talking about the air only. So mass balance on the air. So total mass inside the system, okay, or mass going out. So this is one and the same thing, and these both are equal, and we know there is no like addition or subtraction of mass. Whatever the mass is coming from one side is leaving for the another side. So the magnitude and direction are like both are the same. So this is mass flow rate. So we will going to denote it by m dot. So this represents kg per second or mole per second. Okay, so this mass flow rate we can also write in terms of density and volumetric flow rate, that is density multiply by volumetric flow rate, that is q. Okay, so this is kg per meter cube and this is meter cube per second. Okay, so now further we can like if we don't know the value of volumetric flow rate, so we note that this is the circular cross section and this is the diameter, or we can say radius of that the circular cylinder. So in that way we can find out the area of that, and we know the velocity. So we can write this volumetric flow rate such that density multiply by velocity into area, cross sectional area. So this is basically characteristic velocity, and in the case of cylinder, like the fluid flowing through cylinder, this characteristic velocity is like the velocity which is through the axis, like flowing through the axis of the cylinder. So here we are given with the 50 meter per second. In the question itself it is given. Now we can write it as density multiplied by velocity, characteristic velocity, and area. Now area in terms of diameter will be like this is a cylindrical case. So the cross section is a circle. Okay, so the cross section basically circle. So area of circle is pi r square, but in terms of diameter it is pi d square by 4. Okay, so this is the definition of the mass transfer. And now like we are given with the given data, like density is also given at 20 degrees Celsius, velocity 50 meter per second, and diameter is also given. So now we will going to find out the value of all these constants. Okay, so now we can find out the mass flow rate. So now we have substituted all the values of density, like characteristic velocity and the diameter of the pipe, and we have find out the mass flow rate, like the mass flow rate of air inside the system, that is 0.01064 kg per second. So this is the mass flow rate inside going inside the cylinder and like going out of the cylinder. So this is the mass flow rate that we're going to use in the further calculation. Now this is about the mass balance of the air. Now we will going to do energy balance of the air. Okay, to find out some known parameters and some correlations to find out the length of that heat exchanger. So now we'll go for the energy balance. So first of all, energy which is going inside the system at the entrance, because air is at 20 degrees Celsius. So we will take like a reference temperature for our calculation purpose to represent the energy which is contained by the air when it is entering to the cylinder. Okay, so initially we're going to write the heat capacity or heat at a reference temperature, that is T reference. So energy in by air is equal to, that is something Q in, which is equal to mass contained by the air, that is mass flow rate in kg per second, into heat capacity of the air, and the temperature, like the T be in, the temperature of the air, which is 20 degrees Celsius already given, minus this T reference temperature, because we are representing this energy with respect to some reference temperature. So this is a kind of a reference temperature for the calculation purpose. Now energy which is going out. So we are going to represent it by Q out. Okay. So now the thing which we need to keep in mind is that, see, when the air is entering in the cylinder, then the heat it is contained is mCp delta T. But now, because when it is leaving from the cylinder, what happens is the steam loses its energy and give it to the air, and the steam condenses, and the overall energy of the air will going to rise. So how much energy will going to be rise? We're going to write as mass flow rate Cp, that is heat capacity. Now the temperature out, the out temperature what we are having is, that is 90 degrees Celsius, minus again T something reference, and now the heat, the convective heat transfer by the steam to the air, which will be H into contact area, and again the delta T, that is the change in temperature between the steam and that air. So we will going to have a convective heat transfer between the steam and the air. Okay, so this is logarithmic mean of the temperature. Okay, so now we are having the heat transfer coefficient as delta H, and we are going to take the average value of the heat transfer coefficient, and the contact area in this case we are having a cylinder, so the contact area between the steam and the air is this curved surface area. So this curved surface area for a cylinder is 2 pi r h. So the area will be 2 pi r h, and h means in this case is length, so L. And now this delta T Lm we are having. So this can be written as, like in the expanded form, it is something like that. Okay, and now we can also write 2r as d. So this formula can be written as delta, that is h into pi dl into delta tlm. Now this delta tlm is basically the logarithmic mean of change in temperature, because when the steam is going from this side to the other side, there is a mean temperature difference between the air and the steam, because the steam temperature is reducing and the air temperature is rising. So we will not have a definite value between the steam temperature and air temperature. So this delta T should not be constant, otherwise it will have some logarithmic mean value, average value. So in that case we will take, in cylindrical cases we take logarithmic mean. Okay, so we will write this as TB out minus TB in. So this is already provided in the problem, that is 90 degrees Celsius and 20 degrees Celsius, and now divided by ln, sorry, logarithmic TB out minus TW, and this TB in minus TW. And this TW is another a mean temperature between both of these. So we does not need to take care about that. Okay, so the calculation is take care of by itself. So now we will going to balance both of these, because for the energy balance, energy coming in is equal to energy going out. So for air we are going to balance out both of these terms. So mCp TB in minus reference temperature is equal to mCp TB out plus this convection term delta H into pi d in terms of diameter, and then delta TLM. Okay. Now this term we're going to send it on that side. Okay, to reduce the number of terms. So when it comes to this side, we will get a term as MCP, and this will be TB in minus T reference temperature minus TB out minus T reference temperature is equal to delta H pi ideal delta T logarithm. Okay, so now when we open this bracket, this will be plus, and this both reference temperature will be cancelled out, and what we are left with is mCp delta T plus TB in minus out is equal to delta H ideal. So now at the end of energy balance, we get this relation, that is mass flow rate, heat capacity, and the TB out, that is out temperature of the air. In this case, it is 90 degrees Celsius, and input temperature is 20 degrees Celsius, and the delta, this H, the heat transfer coefficient, and that area, and the logarithmic mean of temperature difference between the heat exchanger. So now we're going to substitute the values here, and like we need to proceed to proceed the solution to find out the L, that is the length of the heat exchanger. So now this M can be like replaced by the formula that we have already written, that is rho and the velocity and the area of the that cylinder. So now M can be written as rho and the characteristic velocity, that is V, and the pi d square by 4 and Cp, and we know this is TB out minus TB in. All the things will be remain same as it is, only we have to substitute is that is mass flow rate M. Now this H pi dl and delta TLM. Okay, so now we know that this pi and pi is going to cancel out, and this d square will be cancelled out, and like anything remaining is so nothing is remaining here. So now what we're going to do is we're going to take out these H heat transfer coefficient and this logarithmic mean that side, so that we can equate the L is equal to this whole term, because we need to find out L. So the whole term should be at the right hand side or left hand side, and we need to find out the L. So we're going to write it as rho V Cp this D 4 H, that heat transfer coefficient, and delta TLM logarithmic mean temperature, and this is TB out minus TB in is equal to L. So like we can write it on that side, that will looks better. So this is L equals to rho V Cp D this 4H, and now we're going to expand this term. Okay, so we already know this term is like that, and there is one mistake, that is this is T input and this is T output. Okay, and the terms will going to remain same, and now we're going to put the T delta TLM, that is logarithmic mean temperature difference here. So in bracket we're going to write this is T D out minus TB in. Okay, and the log TB in minus TW and TB out minus TW, and here we are having TB out minus this TB in. Now we know that in this bracket this term and this terms are same, so we can cancel them. Okay, and this logarithmic mean will going to be go at the top side, because this is 1 upon log, so reciprocal of that will go at the upper side. And now we're going to replace this D on the left hand side to make out the ratio of L by D. Okay, so because we know D and we need to find out L, so we will equate the L by D ratio, which is like more used in the engineering. So we are going to equate this term L by D is equal to rho V, and the remaining terms are Cp 4 heat transfer coefficient log and all the terms. be TB out minus TW and TB in minus TW. Okay, so now we have finalized the equation. Like we need to find out L. Main thing is L. We know D. We know we know most of the terms, and now we need to proceed the question. Now we have a relation of L in some parameters like Cp, velocity, density, and the heat transfer coefficient. And now we're going to proceed further. But now we can see that there is an engineering correlation of heat transfer coefficient like this. Heat transfer coefficient, then density, characteristic velocity, and heat capacity. This is a reciprocal term, so I have written in the simple form. So this is equal to Stanton number of heat transfer. Okay, so I will show you. So this is the Stanton number of heat transfer, that is H upon rho, density, Cp, characteristic velocity. So we have equated these terms here, and this is the relation. And we also know the Stanton number in terms of other important engineering constant numbers, the Reynolds number, Prandtl number, and Nusselt number. We can equate these terms by these numbers. Okay, for the simplification. Okay. So this term is also equal to the Nusselt number upon Reynolds number and Prandtl number. Okay, so now this is because we know that this is 1 upon the Stanton number, so we'll be writing here the reciprocal of that term. So L by D will become, using this relation, L by D become 1 by 4 is separate out from these terms, and this is Reynolds number upon Prandtl number upon Nusselt number, and logarithmic of this dV out dW dV in minus dW. Okay, and now we need to find out the Reynolds number. Prandtl number is already given in the question, and Nusselt number we're going to find out using engineering correlations, the 3 engineering correlations we are having here. Like for the laminar flow, we will use this engineering correlation for the Nusselt number. For the turbulent flow, we will use Datus-Boelter correlation, which is given by this. And also for the turbulent flow, same for the turbulent flow, we can use Seder-Tate correlation, but the conditions are different. Here the conditions are different in the case of Seder-Tate equation correlation, and for Datus-Boelter the conditions are different. Okay, so according to that, we need to substitute the values and we need to use the formula accordingly. And the third one is Whittaker correlation, and the conditions are given there. So these are the 3 correlations for the turbulent flow and 1 for the laminar flow. So for that, to proceed for these formulas, we need to find out the Reynolds number at the first condition. So finding the Reynolds number, in this case, Prandtl number is already given in the question. Okay, so Reynolds number. Okay, so Reynolds number for flow through pipe is characteristic length and characteristic velocity, density of the fluid, and viscosity of the fluid. Okay, so now in this case, as I already told, this characteristic length is diameter of the pipe. Okay, and V characteristic is the velocity that is flow with which the air is flowing through the cylinder. And this is the density of the fluid and viscosity of the fluid. So now substituting these values, and we will going to find out the Reynolds number, and we will see the flow is turbulent or laminar, and then accordingly we will use Nusselt number. So now we have already find out the value of Reynolds number using this relation, and we substitute all the values like density of the fluid, viscosity of the fluid, and diameter, that is characteristic length. Here is the diameter, and the velocity we are having. And now we can see the value is very high, that is 45,000. So this is in properly in turbulent region. We are having the flow is completely in turbulent flow. So now for the turbulent flow, we will going to use the correlations which are given, which are 3 correlations. First is Datus-Boelter correlation, then the Seder-Tate correlation, and third one is Whittaker correlations. So we can use any of them according to the conditions or the situations which are given for each of them. But for this problem, we need to compare all the lengths and the L by D ratio like what we get from all these relations, like Data-Bolter, Seder-Tate, and Whittaker correlation. So, like by comparing them and like by analyzing the solution, we need to make a result. Okay. So for this case, we're going to use this all the three relations. Okay. So for the first one, we're going to use the Data-Bolter correlation. Okay, so for Data-Bolter correlation, we are having the formula of the Nusselt number as the some constant value, then the Reynolds number to the power zero point 0.8, zero point 0.8 or 4 by 5, and then Prandtl number to the power n. And now for this n will be zero point 0.4 when we are like heating, and zero point 0.3 when we are like cooling something. But we know in this case the steam is transferring its energy to the air, so this is properly a case of heating. Like the steam is giving its heat to the air, so this is a case of heating, not the cooling. So we will use n as zero point 0.4 only. So like substituting all the values like 0.023, and the Reynolds number is this 45,000.8, and the Prandtl number is already given in the question, that is 0.707. This is already given in the problem to the power 0.4. And now we're going to find out the value of this Nusselt number. So the value which we got for the Data-Bolter correlation, the value of Nusselt number is 106.88. Now same for the another relation, that is Seder-Tate correlation. And for the Seder-Tate correlation, we will have the formula as for Seder-Tate correlation. The value of Nusselt number is 0.027, Reynolds number to the power 0.8, and then Prandtl number to the power 1 by 3, and here is some another factor of viscosity 0.14. So like before proceeding the Seder-Tate correlation, we will first need to know that this all the properties in this Reynolds number, Prandtl number, and this nu are like correlated at the mean bulk temperature. In this case, that is 55 degrees Celsius, because we need to take the mean temperature, that is 20 plus 90 by 2, that is 55 degrees Celsius. So all these properties, this new Prandtl number properties and the Reynolds number, all the terms are evaluated at the mean bulk temperature. But this term, the nu W, is not evaluated at mean bulk temperature. So now we're going to substitute the values and find out the answer. So using this relation, we have find out like the value of Nusselt number for the Seder-Tate correlation, that is 125.096. Okay, we have like substitute all the values of Reynolds number, Prandtl number, and the viscosity of the fluid and the viscosity of that steam. We have substitute here and we find out the solution. Okay, now the third same for the third relation, that is Whittaker correlation. The value of the Nusselt number is 0.015, Reynolds number to the power 0.83, Prandtl number to the power 0.42, and the same factor. So this formula is almost similar to the Seder-Tate correlation, but like just like uh, normal factor is there for this 0.83 and this 0.42. Otherwise, the formula is almost same, like to remember for the Seder-Tate and Whittaker correlation. Now, again, all these properties are evaluated at the mean bulk temperature except this W omega, that is evaluated at steam temperature. Now we will substitute all the values and find out the answer of Whittaker correlation. So we have find out the value of the Nusselt number for the Whittaker correlation. So now we're going to substitute all these values of Nusselt number in the main formula of L by D ratio. So now we are having this Nusselt number, Prandtl number, it is already given in the question. Reynolds number, it is like we have find out the Reynolds number here, and the TV out we are having 90 degrees Celsius, TB in 20 degrees Celsius, and this TW is for steam temperature, that is 150 degrees Celsius, already given in the question. So now we're going to substitute all the values, and we are going to find out the value of L by D ratio for all the three correlations. So for the first relation of the Datus-Boelter correlation, the value of L by D ratio, that is L by D for Datus-Boelter correlation. So, so now we have find out the value of L by D for Datus-Boelter, for Seder-Tate, and for Whittaker correlation. So the value of L by D for this Datus-Boelter is 25.339, for Seder-Tate is 21.649, and for Whittaker is 29.107. Okay, so we have only changed the Nusselt number because there is only the correlation of Nusselt numbers different in all the three relations. So only the Nusselt number is different and all the things are same. Okay, so this is the B input of the air. This is the steam temperature, 150 degrees Celsius. This is the output temperature of the air. Again, the steam temperature. So all the things are same in all of that, but only the Nusselt number and the magnitude value of the Nusselt number is different in all the three relations. And according to that, we get the L by D ratio of all the three relations according to that. So now we know L by D, so we can find out the length like by just multiplying the D into the that number. So now the L by D, so the L for the Datus-Boelter and Seder-Tate and Whitman, the all the three relations we are having here, like multiplying by the diameter, that is 1.5 centimeter for this case. So so finally we got the length of all the three heat exchanger for the three correlations. So for Datus-Boelter it is like at the middle one, and lowest for the Seder-Tate, and it is highest for the Whittaker correlations. And the reason behind that is that in the Whittaker correlation, we are having some extra factor of this 0.83 and 0.42 in comparison to the Seder-Tate correlation, that is having a 0.8 and 1 by 3 power. So the only difference is that, and like nothing more than that. So these are the three values we got from the Seder-Tate correlations and that the Datus-Boelter and Whittaker correlations. So this is the analysis of the length of the heat exchanger. Now we are having the second part of the question, in which it is saying that. So in the second part, it is saying that discuss the effect of the surface roughness on the length of the pipe. So for that, we need to relate the length of the pipe with the surface roughness. Like there should be a relation for the surface roughness, that is E, that is the surface roughness we use in the fluid mechanics. So the formula which we are going to use here to find out the relation of surface roughness and the length of our system is this. Okay, so we are having the L by D ratio, that is equal to the engineering correlation we are having here. So now we can find out the value of the L by D in terms of the surface roughness. Okay, so now we'll have our engineering correlations as this, and now we can correlate the surface roughness by writing this formula as L by D is equal to 1 by 4 the Reynolds number, Prandtl number, Nusselt number, and then logarithmic of T B in, T B out, minus TW minus TW. Okay, so this is the basically the correlation which we are having, and now we know that at the starting of the problem, I have told you that this is the Stanton number. Okay, so this is the Stanton number for heat transfer. So we can write this is the reciprocal of Stanton number, actually the Nusselt number by Prandtl number and Reynolds number 1 upon Stanton number for heat transfer and this logarithmic term. Okay, and now to find out the relation of friction factor or moreover the surface roughness, because surface roughness and friction factor are correlated. So for that we need to go in the Chilton-Coleman analogy, which says that F by 2 is equal to Stanton number of your heat transfer into Prandtl number to the power 2 by 3 is also equal to Stanton number for the mass transfer into Skinner's number to the power 2 by 3. So here we are analyzing for the heat transfer correlation. So we will use this part. Okay. So now we are having this Stanton number heat transfer. So we will take this Prandtl number on that side, and we can substitute the Stanton number of heat transfer with the F by twice of Prandtl number to the power 2 by 3. We are going to use this relation here. Now by substituting the value L by D is equal to 1 by 4, and now this we can substitute the value, then we are having is F into 2 times Prandtl number to the power 2 by 3 and the logarithmic term. Now we can cancel out this like the constant terms, and now we are having the friction factor friction factor correlation with the length of that heat exchanger. Now we know that the relation of friction factor and the relation of our surface roughness could be like analyzed by 1 upon root f is equal to minus of 4 logarithmic of, and this is surface roughness, the relative surface roughness, and some constant is there. And now the value of this constant, that is a, is can be written as okay. So the main relation that we are having is these three relations. Okay, so like we know the Reynolds number, so we know the Reynolds number and we know the diameter of the pipe, and if we know the surface roughness, then we can find out the value of this constant. Okay, with the help of Reynolds number, diameter and surface roughness, we can find out this constant A. Then we can substitute the value of this constant here in this formula, and like we know the Reynolds number, we know this constant now, and this E by D ratio, relative surface roughness, we can find out the friction factor, and by substituting the value of friction factor here in this formula, we can find out the value of length. So like if we want to change the surface roughness or relative surface roughness in a system, then the change or the impact of that change we can like calculate, or we can see by this relation. So L can be related by surface roughness with this correlation. Okay, so now we can use we will use here different surface roughness like E by D ratio, that is relative surface roughness like 0.0001 or 0.002 or till 0.00, like for example 4, and we will see how like the value of f are changing and how the L by D ratios is changing, and at last how the value of L is changing with the surface roughness or moreover the relative surface roughness. So like by putting these value, you can find out the value of friction factor L by D and L, and then we can analyze the like the analytical solution or the like that how the relative surface roughness is changing with the length or having an impact on the length, we can find out. So now for the different values of E by D, that is surface relative surface roughness, we have find out the value of friction factor using this formula, and from the friction factor we have find out the L by D ratio for different friction factors with the help of this formula. Okay, we've only changed the value of friction factor. We already know the Prandtl number and all the temperature change. Okay, so we all only find out the friction factor from using this formula, using the surface roughness and then L by D ratio, and simply multiplying the L by D ratio with the diameter, we have find out the value of length. So here is the analysis. For the like when we are increasing the relative surface roughness from 0 to higher number, then the length of the heat exchanger is decreasing. Okay, but it is not decreasing by the like by a large amount, but like we are increasing the relative surface roughness with the like a 0.0001, and there is a significant decrease in the length of that heat exchanger. Okay, so this is the one of the analysis, and this could be explained by with the help of that when the friction factor, when the surface roughness increases, the friction factor also increases, and when the friction factor increases, the power consumption or the heat dissipation here or heat consumption increases, because from this relation, the Stanton number heat transfer correlation with the friction factor, and we can expand this form as the the heat transfer coefficient, the density Cp into characteristic velocity. We can see that with this relation, the friction factor is directly proportional to the heat transfer coefficient. So with the help of this relation, we can analyze this relation also, that with the help with the increase of relative surface roughness, the friction factor increases, and with the increase of friction factor, heat transfer rate increases because heat transfer coefficient also increases, and then we are having the then we require less contact, or the less length or less volume for the contact of steam and the fluid, so we require the less length of the pipe. Okay, so here is the analysis of this question.